Hello, welcome to the solutions video for lesson 1 in unit 1 for the Ready, Set, Go. So the Ready section of this tells us inverse operations undo each other. For instance, addition and subtraction are inverse operations. In mathematics, it is often necessary to undo several operations in order to solve for a variable. So this set of problems wants us to complete the statement by identifying the operation used to undo the equation. So the first one we see 24 equals 3x, so it says undo multiplication by 3 by dividing by 3. Multiplication and division are inverses of each other. They undo each other. Now we can also think of multiplying by its reciprocal, 1/3, so there are other ways that we can think of this. 8 is 24 over 3, and 3 over 3 becomes 1x, or just x. Okay, our next one, it says undo division by 5 by multiplying by 5. Again, there's other ways we can consider this if you had something else in mind. But here, if we multiply both sides by 5, our 5 over 5 reduces to 1, which is what we want, 1x, or just, again, x. Negative 2 times 5 is negative 10. Here we have undo addition 17 by subtracting 17. And for all these, I really should be writing to both sides of our equations, right? We always want to balance the equation. I'm just kind of using shorthand. So those 17s, they add to 0, so it's really x plus 0, just x. 20 minus 17 is 3. We can always plug these numbers back into check since we do have an equation. So undo the square root by squaring both sides. Again, there's other ways to phrase this. You could say raised to the power of 2. So if I square a square root, remember we need 2 of something to get rid of it, so this is telling me I now have 2 x's, which gets rid of that square root. So it gives me just 1x, and 6 squared, or 6 times 6, is 36. Okay, here we have a multi-step problem, right? So we want to do order of operations, or sort of, we want to make sure we get rid of this outer thing first. So I see a cube root. So we need to cube, or you can think of it as raised to the power of 3. So we want to raise both sides to that power of 3, or cube them. That's going to cancel or reduce out that square root sign. So that's going to leave us with just x plus 1 equals, well, 2 cubed is 8. So now last thing to get that 8 by itself is to subtract 1 from each side. Right, that gets us our 0. So we end up with an x equals 7. So then we subtract 1. Okay. Undo raising x to the 4th power by taking the 4th root. Again, we could also use another power. Raise to the 1/4, we can use the reciprocal power. And I'll show what both of those look like. Right, so if I were to take the 4th root, I use the radical symbol in both sides. I'm going to do the principal root of 81, which is going to be a positive. Well, 81 is 9 times 9. Remember, I need 4 of the same number. So I can break that down to 4 3s. So x equals 3. Now the other thing we can do is, instead of taking the 4th root, we can actually use our exponent rules. Raise this to the 1/4 power, because when we have exponents, they multiply when it's a power raised to another power. So 4 times 1/4 becomes x to the 1, or just x. 81 to the 1/4 is the same thing as the 4th root of 81, which becomes 3. Okay, So those are the ready problems. Oh, we got one more, actually, one more ready problem. So here's another one that has multiple steps, right? I see x minus 9, but it's stuck in my parentheses. So the first thing I have to do is get rid of that square. So undo squaring by taking the square root. Again, you could also use the reciprocal. So raise to the power of 1/2. That would get rid of the 2. But we'll do the square root method for this one. So I square root both sides, and I'm going to again do the principal root here. X minus 9, because that's the square root, they undo each other. And the square root of 49 is 7. So now I still have this minus 9 attached to my x. So if I add 9 to both sides, so add 9, I'm going to get x totally by itself. And 7 plus 9 is 16. Excellent. Okay, so our ready problems are done. We practiced completing this statement to isolate x. So let's look at the set problems. It says Carlos and Clarita have a pet sitting business. When they are trying to decide how many of each dogs and cats they could fit into their yard, they made a table using the following information. Cat pens require 6 feet of fencing, 6 square feet of space, while dog runs require 24 square feet. Carlos and Clarita have up to 360 square feet available in the storage shed for pens and runs, while still leaving enough room to move around the cages. They made a table of all the combination of cats and dogs they could use to fill the space. They quickly realized that they could fit 4 cats in the same space as 1 dog. So that actually becomes the most sort of relevant information to us, because that means we have a constant difference. Which tells us that we are dealing with a linear relationship. So this linear relationship, that constant difference, that rate of change is not changing over time. It's remaining the same. 4 cats in the same space as 1 dog. Okay, so use the information table to write 5 ordered pairs that have cats as the input value. So cats is the input. Now, you might be thinking that as where sort of the x usually is when we're thinking of equations, the independent variable, and dogs the output. So cats as the input means that's our first component. So first component. Now, it says, write 5 ordered pairs. Looks like we have, counting quickly, 16 possible pairs. So we're going to pick 5. I always like to pick ones with, let's say, zeros in them. So I want my cats to be the first component. I'm going to write these in a set. So 0, 15 is going to be my first ordered pair. 0 cats to 15 dogs. And then I'm just going to spread them out. There's no sort of right or wrong. It just says pick 5 random ones. So as long as you're picking some from this table and putting them where your cats is your first component, then you're all set. Let's pick 32, 7. Again, I'm just spreading them out. So there's 3 right there. Let's pick 44, 4. And then lastly, let's go with 60, 0. There's no really rhyme or reason to me picking those particular 5. So if you picked a different 5, that's perfectly fine. Now it says write an explicit equation that shows how many dogs they can accommodate based on how many cats they have. So the cats is our independent variable here. That's the thing that determines how many dogs are available. Right? The number of dogs will be a function of the number of cats. So once again, cats is our input, which means that's the variable we want to see in the equation where that x normally is. So, and it tells us we can use this form. So since we actually already know our vertical intercept, right? Vertical intercept, meaning when our input is 0, right here, is 0, 15. Why not use it in that sort of y equals mx plus b form? It's not the only option, and sometimes when we see explicit equation, we want to write it with a common difference in our n-1, but right now we have a vertical intercept and we know our slope, right? So that rate of change, we can call this rate of change a slope since we determined that this is a linear relationship, right? Our input is always on bottom. So it's the change of the dogs over our change in cats. So if we look at this, anytime our dogs decreases 1, so if we decrease 1 dog, our cats increases by 4. So our rate of change is -1/4. So we have our rate of change, or a slope, that's our m, and we have our vertical intercept, b. So I'm going to do d equals f of c -1/4 c plus 15. And if you're not confident in this, pick one of the numbers from above and plug it in and double check. So let's check this. Let's check with 2010. Those are nice numbers, right? If we have 20 cats, that means we should have 10 dogs. So I'm going to set it equal to dogs, 10. So 1/-1/4 times 20 plus 15, that should give us 10. -1/4 times 20 is -5. -5 plus 15 is, in fact, 10. We know we did it right. We'll kind of just separate that off to the side. So that's a nice little reassurance. So we didn't need to do that, but it never hurts to check our answers. All right, let's go down. It says, number 10 says, use the information table to write 5 ordered pairs, this time that have dogs as the input value and cats as the output. So it doesn't change the pairings, but it changes what the first component did. So dogs is the first component. Our input is always written as the first component. So I could honestly use the exact same pairings, right? I could do 15-0, but this time this is our dogs and this is our cats, right? So the pairing's still the same, just the order that I represent the number is different. I could do 11-16, right? I can do 7-32, and I can do 4-44, and then lastly 0-60. I did not have to pick the same 5. I just chose to. So now it says write an explicit equation that shows how many cats they can accommodate based on on how many dogs they have. The number of cats will be a function of the number of dogs. So this time dogs is the input. And I'm using shorthand, right? And the number of dogs is the input. I'll underline that whole thing. Number of dogs is our input. Once again, we actually already know our vertical intercept. And I'm not calling it y-intercept right now, simply because there's no y's in this equation. We have c's and d's. So our vertical intercept, right, that's actually over here. This time when dogs is 0. When there's no dogs, there's 60 possible cats. So 0-60. Our rate of change, again, more commonly called slope when we're dealing with a linear equation. Well, this time we want the change in the number of cats over the change in the number of dogs, since dogs is now representing our input. The change is still the same, it's just how we represent it. So now, if we think we're increasing by 4 cats, that means we have to decrease by 1 dog, or -4. So again, we have our vertical intercept, we have our slope. Let's go straight into slope-intercept form. C equals g of d, which equals -4d plus 60. Now again, you could pick the same point if you want. Plug in, if we plug in 10 here, -4 times 10 is -40 plus 60. That does give us 20. We know we have 10 dogs when there's 20 cats. So that equation checks out. We are all set to move on. Just going to circle both of those equations. So same information, just paired differently. Okay, let's go on to our next problem. So this is still looking at the same question. It says, look back at problem 8 and 10. Describe how the ordered pairs are different. So we already talked about this, right? 8 and 10 had the two ordered pairs. So when the cats was the input, I should say, let me be better about this. When the number of cats was the input, the value that represented cats was listed first. Was the first component, I'll call it the component, the first component. Listed. And vice versa, right? When the number of dogs, so when the number of dogs was the input, well, that's when the value that represented dogs was the first component. The pairings did not change, right? So it says, how are they different? So I won't write that the pairings didn't change. The pairings didn't change, though. It's just which one was listed first. Okay. Now it says, look back at the equation you wrote for problem 9. Describe the domain for D equals f of c. So problem 9, right, we said D equals f of c is let's just rewrite it, equals negative 1/4 c plus 15. So domain, right, that's everything we can input. So all possible input in our case, the input is cats. So all possible input values of the cats. Now, there's lots of ways you can write domain. We could have 0 cats. Of course, we can always have 0 cats. And then the most number of cats we could have was actually 60. If we look at our table, we see that it goes up to 60 possible cats before we sort of run out of space. So the equation itself, if I only had the equation, I would say it's negative infinity to infinity, all real numbers, because it's linear. So theoretically, you know, that linear equations go on and on and on. But ours has some restrictions because of the size of the pen. So we can only have up to 60 cats. Now, there's other ways to write this. You can write this in interval notation, right, 0 to 60. You could write it as a set, right? We could say the domain such that, and I'll use inequalities here in my set. You don't have to. There's other ways to do it, but I think it's a nice, quick way to represent it. So there's lots of different ways you can write it. But we are limited in how many cats we can have because of the size of the pen. So describe the domain, part B says, describe the domain of the equation C equals G of D that you wrote in problem 11. So remember when we did this one, C equals G of D. This time we had negative 4D plus 60. So here, our dogs is the input, number of dogs is input, and remember domain is our input value. So this time we could have 0 dogs, and because the dogs take up more space, the maximum amount of dogs we could have is 15. Again, we can go to our table and look at our dogs, see that we have 15 or 0 as our sort of range here. Now, I'm using the word range because that's a span of numbers, but in this case, it is the domain. So, again, there's lots of ways to write it. I won't show all 3, but I'll show interval notation here too. Okay, so what is the relationship between them? Well, they're actually the range of each other. So I'll phrase that in a little better. When cats is the input, when the number of cats is the input, is the input 0 to 15 for dogs is actually the range. Right? It says 0 to 60 for cats is the domain, but 0 to 15 is the range, right? When the number of dogs is the input, zero to 60 for cats is the range. So when we switch our input and output, we also switch our domain and range. So when I asked you to find the domain, right, when I asked you to find the domain of this equation, we were actually also finding the range of that first equation and vice versa. So that's a new way we can actually find range, is finding the domain of our inverse. So that's something we'll talk about in lessons coming up. All right, so our last section, go. So this time, let's just do some color changes here. It says the functions f of x, g of s, and h of x are defined as f of x equals x. So this is an equation where really just y and x are equal. The input and output are always going to be the same, so those ones will be pretty quick. G of x is 5x minus 12, and h of x is x squared plus 4x minus 7. So let's talk about these f of x problems first. So I see f. Now notice the output of f of x is whatever is equivalent to the input. So if our input is 10, our output is also 10. Nice, quick, and easy, and that one's done. Here our input is -2, so it's going to have an output of -2 as well. Here, f of a, our input is a, that means our output is also a. F of a plus b, well, a plus b is our input, so a plus b is our output. So those ones, there really wasn't much algebraic manipulation. Let's go to our g of x problem. So remember, g of x is 5x minus 12. I'm just going to rewrite that. Right, g of x equals 5x minus 12 to keep that sort of in the forefront of our thoughts. So here, g of 10, so when I input 10, I want to do 5 times 10. I replace, this goes where x was, minus 12. So let's go, I guess I'll work horizontally. So 5 times 10 is 50. 50 minus 12 is 38. I don't have to rewrite it, but just so our answers are nice and neat and clear, I'll rewrite it that the input 10 gives us an output of 38. Okay, g of -2, so 5. I'm going to replace my x with -2, right? That's where the x was. Minus 12 still. 5 times -2 is -10. -10 minus 12 gives us -22. So g of -2 is -22. So the input -2 gives us an output of 22. All right, let's carry on to question 20. So here are those problems again. Just kind of copy them over so we wouldn't have to flip back. Let me organize this. There we go. So g of a. So there's not a number in here. We can't do 5 times a to make it, you know, a different number. So we just rewrite it as it is. I don't need the parentheses. It doesn't hurt to put them. but I'm just going to replace my x with a, and that's all we can do in this one. That's as simple as we can make it. 5a and 12 are not like terms, so I can't combine them. So our next one, 5 times a plus b is the whole input, so I want to make sure that whole thing is getting multiplied by 12. So here the parentheses are really important. So let's make sure we distribute into this 5, into the 5 into the set of parentheses. So 5 times a is 5a, 5 times b is 5b. Again, none of these are like terms, so that's really as simple as I could write this. So g of a plus b equals 5a plus 5b minus 12. And there's nothing really that indicated we had to distribute that 5. Let's reread the directions just to make sure, right? It says calculate the indicated function values in the following problem. So it didn't necessarily say which form to write our answer in, but it's good practice to expand our parentheses, so we'll do that. Okay, H, let's pick another color to go with. Okay, so we'll do H here. So H of x is equal to x squared plus 4x minus 7. So just make sure we're squaring really carefully. 10 squared plus 4 times 10 minus 7. So 10 times 10 is 100. 4 times 10 is 40. And then we have that minus 7 kind of tacked on the end. So it doesn't matter which order you add these in. I'll do my 100. I'll add these first. So plus 33. So I get 133. So for an input of 10, we get an output of 133. Okay, negative 2, we want to be extra careful about parentheses. Negative 2 is the whole input, so I need to make sure I square that whole number. Negative 2 times negative 2 does give us a positive 4. 4 times negative 2 gives us a minus 8. And then we have the negative 7 at the end, right? This time, just to show I can do it in a different order, I'll add those first two together. So negative 4 minus 7 is negative 11. You can do it in one step if you feel more comfortable, but I find that people tend to make fewer mistakes when they add in multiple steps. So input of negative 2 gives us an output of negative 11. Here, h of a, there's not much simplifying we can do, so we're just going to replace our x with the a, and that's all we can do. So instead of x squared plus 4x minus 7, we get a squared plus 4a minus 7. Now 25, again, a plus b, we have to be a little bit more careful. So all of a plus b gets squared, plus 4 times a plus b minus 7. So this one, I'm going to do vertical for this one, because this is a super common mistake that I see. I see a lot of people see this, and they write a squared plus b squared. But we can't just distribute that 2. What that 2 means is it's a plus b times itself. A plus b times a plus b. So we actually have to make sure we're distributing every term in this first set of parentheses to every term in that second set. So I'm going to do a times a is a squared. And then a times b is plus ab. So we're going to do the same thing for this second set of parentheses, or for this second term. So b times a is plus ba, or I'll write it as ab again, it doesn't matter. And b times b is plus b squared. So that's all coming just from a squared plus b squared. So be really careful. Here, I'll go back to this blue. We have to distribute the 4. So we get plus 4a plus 4b. So I'll keep copying that down. And the 7 is still just kind of tacking on at the end. So now let's see if we have any like terms here. There's no other a squared terms. So I'm going to rewrite our h of a plus b. There's no other a squared terms, so it stays by itself. notice I have an AB plus AB, so that becomes 2AB. The order where you put your terms doesn't matter. I'll do my b squared term next, I suppose. There's no other b squareds, and there's no other for a or for b. Right? There's no other terms with just an a, and no other terms with just a b. So we're looking for things that, even though this term has an a and a b, it's not only an a or only a b, so they are not common. They're not like terms. I can't add them together. So this is actually as combined as possible. We can't combine any of those terms. None of them are like terms because they don't have the exact same number of variables. I think that's it for this Ready, Set, Go. So hopefully you found that helpful. And thank you for watching.